Density. Density is a measurement we're going to use quite a bit in this class. It is the ratio between mass and volume. So in other words, you could write it like this. Density equals mass divided by volume. So it's a kind of a ratio. Because these are different types of units, their units can't cancel. So you'll have units of mass divided by units of volume. So for liquids, the units are grams per milliliter. And for solids, for whatever reason, the convention is to write grams per cubic centimeter. But remember, a milliliter and a centimeter cubed are the same. So in other words, what does this mean? If you have a density in grams per cubic centimeter, so let's say we had 15.2 grams per cubic centimeter is the same as 15.2 grams per milliliter. You can just change those because a centimeter cubed is a milliliter. The idea here is if something is very dense, then a very small volume of it has a large mass. So things that are dense, like a brick is very dense, right? Not a big volume, but it's still quite heavy. Compare that to, say, a styrofoam brick. Styrofoam can be quite big, but it's still very, very light. Okay, takes up a very large volume, but is very light mass. Okay, this works exactly like what we were talking about before, where we were dealing with units that have two parts a lot of the times. You want to think of density as a conversion factor. Between mass and volume. That's its purpose. So in other words, if I know the density and I know the mass, I can always find the volume. And if I know the density and the volume, I can always find the mass. And of course, if I know the mass and the volume, I can always find the density. Just make sure you don't get these upside down, okay? Always mass over volume. All right, so let's say we have an example here. Let's say we have an empty graduated cylinder. And our empty graduated cylinder here that's going to be our graduated cylinder, has a mass of 22.57 grams. That's its mass. I would get that by putting it on a scale and weighing it, essentially. Now let's say I add some liquid to it. We don't know what the liquid is. Let's be some blue liquid. And whenever you add matter, what's going to happen to the mass? The mass will have to go up or down. Does something's weight go up or down? If I hold my cat when I get on the balance, it's going to make my weight go up. Yeah, definitely. So I put 7.25 milliliters of liquid. That's the volume, right? If I read that, it would be 7.25 milliliters. And now its new mass is 30.79 grams. Now, let's be very clear. The density of the liquid, and this is where you have to be very careful that you don't go wrong. It's not just mass over volume, it's mass of the liquid divided by volume of the liquid. Has to be the same substance. There's two things in this picture, though. There's not just the liquid, there's also the cylinder, the container. So make sure that you don't count the container. You can't count the container. So what is the mass of the liquid? Well, this is what? This is the mass of the, what is that the mass of? 30.79 is the mass of the
liquid
graduate cylinder.
container.
Yeah, that's the cylinder plus the
Liquid.
Plus the liquid. Good. And what's this?
Just a container.
Exactly. So the mass of the cylinder. So this is where I have to use what's called the method of differences, or mass by differences. How do I find the mass of the liquid?
The one with the mass of the cylinder and the liquid. And then
Exactly. You subtract. Very good. So it's the mass of the cylinder plus the liquid minus the mass of the cylinder gives you what?
the mass of the liquid.
Good, very good. That's called the mass method. That's masses by difference. You always subtract out the container. You have to use a container, right? Because you can't weigh a liquid without it spilling all over the place. So you have to put it in a container. Okay. So the mass, that's what's that going to be? Cylinder plus the liquid is 30.79 grams. The container is 22.57 grams. So when we subtract, 9 minus 7 is 2, 7 minus 5 is 2, 30 minus 22 is 8. That's the mass of the liquid. So make absolutely sure you're not putting either of these in the numerator. It's this minus this. Good. So what's the density going to be? What divided by what? Mass of the liquid is
8.22 grams.
good. And the volume? What's the units of the volume?
Great.
Yeah, be very careful. Mass is the grams part. What's the volume?
7.25 milliliters.
Excellent. 7.25 milliliters. Good. Can those cancel or no? Grams and milliliters. They are different kinds of units, so they cannot cancel. Good. So now we divide. What's the whole point of division? It's to turn the denominator into what number? When you divide, the denominator becomes
Numerator.
1. Just becomes 1, right?
Where?
Yeah. So 8.22, because the calculator only gives you one number back. So 7.25 It just gives you a single number. So that means the denominator is 1. Gets rid of the denominator. So I'm getting 1.13. And I'll write that as grams per milliliter. In other words, 1.13 grams for every 1 milliliter. So as a conversion factor, let me just rewrite this a little differently. Yeah, I'll deal with that in a later problem. I don't want to deal with that right now. Okay. Okay, another question here that's related. Say we have a 73.43 gram cube of gold, and we drop into a graduated cylinder whose volume reads 27.8 milliliters. In other words, it's got water, 27.8 milliliters of water. After it sinks to the bottom, what will the volume reading be in the graduated cylinder? So the gold has this density, 19.3 grams per cubic centimeter. So in other words, if I had, or not in other words, if I had a picture here. So here's my cylinder. Well, let's make it a little bigger. And before, its reading is what? Its volume is 27.8 mils. And then this is my before. And then after, what always happens to the volume when you put something in it? Except for maybe a sponge, the volume will go up. You've got your gold down in the bottom. So we want to know how many milliliters this is. So if I added the gold to the water, what is the volume of the water before and after? It's still 27.8 mils, right? The gold doesn't suddenly change into water. So I have 27.8 milliliters here, and then the water is 27.8 milliliters, but it rose by the volume of the gold. So this number right here is going to be what? This is the volume of water plus the volume of gold. We already know the volume of the water. It's 27.8 milliliters. But we don't know the volume of the gold. So I am going to treat this as a conversion factor. In other words, 19.3 grams of gold. I can't say is equal to 1 centimeter cubed. but I can say they are equivalent, which is just as good. That symbol means equivalent. In other words, they don't have the same unit, but if I worded it, what I can say is this. In words, I can say, well, 19.3 grams of gold isn't a centimeter cubed because they are different units. But I can say if I have 19.3 grams of gold, its volume must be 1 centimeter cubed. They are equivalent to each other. They are the same amount of gold, but just in different types of units. Just like in money, a certain amount of money represents a certain amount of goods. A certain amount of money represents a certain amount of gasoline at a particular gas station, right? If you have this much money, you can get this much gasoline. The money and the gasoline aren't equal to each other, but they are equivalent. They can be interchanged for one another. All right, so a centimeter cubed is the same thing as what? This was a very big deal. You need to make sure you remember this. Centimeter cubed is the same as a what unit? A milliliter. Yeah. So let's change this into 19.3 grams is equivalent to 1 milliliter. And now all we have to do is find the volume of the gold. So that's a conversion. I've got 73.43 grams of gold. I need to convert grams of gold to milliliters of gold. So I just fill in my numbers. What goes in front of grams of gold? 19.3. What goes in front of milliliters? 1. And so now using my unit method here, those cancel. And I can easily find milliliters of gold. 73.43 divided by 19.3 is 3.80. Densities are not exact numbers, by the way. They have significant digits just like everything else. So if I gave you 19.3, that's only 3 significant digits. So 3.80. Good. So the volume reading is going to be exactly what we said here. 27.8 plus the volume of gold. And what is that? 31.6. This goes to the, remember now we're adding. This goes to the tenths. This goes to the hundredths. We must go to the tenths. 31.6 milliliters. $31.6 milliliters. Any questions here? I'm hoping that wasn't too hard. You also could have found this by just using the equation, density equals mass over volume. So you could have just rewritten it like this. You're trying to find the volume, right? So you could multiply both sides by V and divide both sides by D, and that would rearrange to volume equals mass over density. And isn't that what I ended up doing? I took the mass and divided it by the density. That would have worked as well. But I want you to get really used to using this unit conversion method instead. We actually call this dimensional analysis because we're going to use it in ever longer and longer problems. It makes life much easier if you do it this way instead of solving step by step by step. Percentages, temperatures, yeah, okay. So this will get me through chapter 2. I don't think the book really goes into percentages at this point, but they're so important that I want to make sure that we at least address the issue. So remember, I already said per means for every one. Cent means 100, like century, 100 years. So percent means for every 100. And specifically, it means when you say the percent of something, it means the amount of the whole of the part, the amount of the part for every 100 parts of the whole, the amount of the part for every 100 parts of the whole. And what that means, what is a part, what is a whole? It depends on the context. You have to figure it out from what's being described. So let's say I have a mixture and it's 15% iron by mass, meaning grams. The part is the iron, 15% iron. Whenever you've got, a word following it, you know that that's the part, 15% iron. What is the whole? What word in this sentence is the whole?
Mixture.
The mixture, good. So there's 15 parts of iron for every 100 parts of mixture. Okay. By mass means we can do this with grams, or we could do it with kilograms, or we could even do it with pounds. So long as we're on Earth, we can do it with pounds. Okay. And we're not going to be going off the planet. So if we wanted, we could change this to any units we want. Okay. So we can use any mass or weight unit we want, so long as they're the same. You can't do pounds on one side and grams on the other. We could even do tons. So what that says is there's 15 grams of iron for every 100 grams of mixture, or 15 kilograms of iron for every 100 grams of mixture, or kilograms of mixture. I need to write the word of. Or I could say pounds even, 15 pounds of iron for every 100 pounds of mix. I could not say 15 liters of iron for every 100 liters of mixture. Why is that not allowed? Why is that?
Because there's liters for volume and then
Excellent.
And we're dealing with mass.
Yes, liters is volume, and we're dealing with mass. Now, the reason I can do pounds is because pounds is just mass times a number. But liters, these won't have necessarily the same volumes. Okay. So yeah, exactly. You can't do it with volumes, but you can do it, and you couldn't do it with lengths, for example. It wouldn't make sense to say 15 meters of iron or anything like that because we can't measure them that way. So, but you can make any mass or weight unit you want. So I could have said 15 tons of iron for every 100 tons of mix, 15 milligrams of iron for every 100 milligrams of mix. And so usually we're doing them by mass. When someone doesn't give you a unit, if they're sloppy, you can usually assume they mean by mass. It's very rare to do one of these by volume. Not very rare, but it's comparatively rare. Okay, so example, the mineral calcite is 40% calcium by mass. So in other words, that means what? There is 40 grams of calcium for every 100 grams of calcite. That's the whole. Okay. So what mass of calcium is in 1.55 kilograms of calcite? Well, if I've got 1.55 kilograms of calcite, remember, what does this saying? This sentence says what is a number? 40% calcium by mass means there are 40 grams of calcium for every 100 grams of the whole, which is calcite. Or I could say 40 kilograms of calcium for every 100 kilograms of calcite. So in the denominator, I'm going to put kilograms of calcite because that's what I want to cancel. Notice you don't want to, when you're dealing with two or more substances, you need to write down the names of the substances. You can't just leave it out. Otherwise, you're being unclear. So for every 100 kilograms of calcite, you have 40.0 kilograms of calcium. That's what that means. So kilograms of calcite cancels with kilograms of calcite and leaves you with kilograms of calcium. Now, I know some people said, well, can't I just multiply by 0.4? Sure, but I need to see the work. I need to see that that your units are canceling. So 1.55 times 40 over 100 is the same as times 0.4. So I'm getting the calculator says 0.62, but why is that the wrong answer? What is it not taking into account?
The number of sig digs.
Good. So there's 3 sig digs here, 3 sig digs here. In a percent, you always ignore the 100. That's not considered part of the sig digs. This is the sig digs, the 40. So 3 and 3. So how do I make this have 3 sig digs? 0.62.
0.
0. Good. Kilograms of calcium. All right, and then let's do part B. We want to know what is the mass of a block of calcite, which has 13.5 grams of calcium. So I'm just doing a conversion from grams of calcium to grams of calcite. So it's like the last problem, but just kind of in reverse. I have 13.5 grams of calcium. So remember, we've got two substances, calcium and calcite. We don't even want to abbreviate them because it would be easy to confuse them. In the denominator, I want grams of calcium to cancel. And I want grams of calcite in the numerator. So let's go back in our conversions. We had 40 grams of calcium is 100 grams of calcite. So 40.0 grams of calcium. It's okay if you write this as its reciprocal. That's totally fine, so long as you keep the number with the unit. 40 grams of calcium is 100 grams of calcite. So grams of calcium. Cancel. And now we go to the calculator. And the calculator is giving me 33.75. We need to round that to, this is 3 significant digits. This is 3 significant digits. So 33.75 to 3 significant digits would be 33.8. And the unit that's left over is
kilogram calcite.
grams of calcite.
Yeah, gram.
Very good. By the way, on exams, I would appreciate it if you'd, underline your answers. So I know, if you have a lot of work where I need to be going first, or putting them in a box or something like that, I do need to see your work. And in this class, it's very hard to get the right answer without the right work. In Chem 140, there are times when people get, they get the right answer, but they still don't. I don't give them credit because it's really weird. In Chem 140, you can get a wrong divided by a wrong, and the wrongs cancel out, and you get the right. It's weird. 2 wrongs do make a right sometimes in that class. But they'll make one number 100 times too large. They'll make the next number 100 times too large, and they cancel out. Or in like a long series of calculations, they make an error here that then cancels out here, and then it's all just there. So anyway, that doesn't usually happen in this class, but I do need to see your work. Especially because if you get the wrong answer, but your work is right, I'll usually just, it's an 8-point question. I might take off only 2 points and say calculation error. Because if your work is right, you've done most of what you need to. You just need to learn how to deal with your calculator a little bit better. So I do look at the work a lot and give you partial credit if the work looks good. If you don't give me any work, then number one, I can't give you credit because, especially while we're on the pandemic, I know that there's websites out there that can do the work for you, or the calculations if you know where they are. And I need to see the work that matches up with it. So always show me your work. That's the most important thing to me, is that I see your work. And if you get the right answer, good, you get full credit. You get partway there, you'll get part of the credit. Okay, converting temperatures. is not going to be a really big deal for right now. So I'm not going to spend a lot of time on that. The differences between converting temperatures and all these other conversions, everything up here is multiplication. Temperatures tend to be by additions. Okay. We will need to do Celsius and Kelvin a lot, a ton. But you know what? We're not going to need this until chapter 11. So I'm just going to ignore it because a lot of people won't remember when we get to chapter 11 anyway. So let's just come back to this in chapter 11. Okay. You're fine with it. I'm fine with it. Which is on gases. Because all the temperatures have to be in Kelvin when we get there. But we've got a lot to do before we get to gases. So we'll worry about Kelvin later. As I said, we only use Fahrenheit when we're dealing with the weather. And it's not really going to be often that I'll ask you, what's the weather in Celsius? So there's no real reason for that. So I'm not going to really spend any time on this. I might assign a couple problems on the homework, but it's just using formulas. I would note that the very last page, again, my conversion factor. My speaker keeps getting in the way. There we are. The temperature conversions are already right here. And I will give you them if you need them. They are not marked as something you need to memorize. Okay. We also won't even get into the acid base this semester. I just give those for reference. And pressure we won't deal with, nor energy and power for a while. These won't be until we're about 75% of the way through the class. So we don't have to worry about those yet. So don't memorize these. Or do if you want, but they're not going to be required for a long, or for anything that I'm going to ask. If we are now done with this, we are now through the monster chapter. Chapter 2 is a monster. It's big. It's bigger, I think, than pretty much everything we're going to do except for maybe chapter 7, which is chemical reactions. Accuracy and precision. You know what? If I get a time, I'll talk about that later. But this is something that we talk about in Chem 130. I don't think I really need to go over it this semester. In fact, I don't remember if the book goes over this, and I know they'll go over it in Chem 130, so it's not that big a deal. Let me just do a quick introduction because we've got a few minutes. Data is accurate when the data are close to the true or correct value. And it's precise when you get data that is reproducing the same number over and over and over. So for example, this is so annoying. Where is my chapter 2? 20. There we are. So just to show you this, and this comes right out of the Chem 130 book right here. You're accurate if you're getting the true value. But if you're getting the same type of values over and over, you are precise. So let's look at a game of darts here. What would be considered accurate for playing darts? What are you trying to do? What is true for darts? You want to try to
target in the bullseye.
Yeah, you want to get the middle. Okay. Okay, so how would we describe player A? If we're playing darts in a bar, which is normally where you'd be playing them, what's probably the best one-word description for person A?
Okay.
50-50.
Low precision and low accuracy.
No, I would say drunk. I think they're drunk, or they're just not very good. This is like me playing darts, even if I'm not drunk. Okay. right? They're not very good. Are they ever hitting the bullseye?
No,
No. Is there any real pattern to anything they're doing?
no,
No. No. Would you want your data to be like this in an experiment? In other words,
No.
all over the place with that pattern? No. Yeah. This is not accurate and it's not precise for a darts. Person B has a lot of potential. Now, person A has a better score than person B. But I bet person B could be a lot better than person A, because what are they at least doing? They are at least,
their darts are basically near.
yeah, all you have to do to person B is say, okay, move a little to the left. Now lean down and you're perfect, right? They are consistent. So what word was consistent? Consistent was precise. Okay. When we say precise, that means you're getting the same values over and over. What that means in chemistry experiments is that you're probably doing what? If you're precise but not accurate, you're probably making an error over and over and over again. And if you can just fix that one little error, you're fine. Correct? It's a matter of tracking down the error or troubleshooting. And what word would we say for person C? They are accurate and precise. They are both. They are accurate because they're hitting the right place and they're hitting it consistently. So they are precise. So accurate and precision are different things. Accurate is you're getting the right value, and precise is you're getting the same value consistently. Now, on most experiments in my class, can you know if you're accurate? If I'm the only one that knows the answer, because that's what I'm testing you on, is can you get the right answer by doing experiments? You don't usually know your accuracy. Only I know your accuracy. Okay. I'll tell you what the answer should be around, so you'll know if you're kind of in the ballpark. But that's one of the ways that we grade you, especially in Chem 130 when you're in lab, is are you able to come up with the right answer by doing your experiments right with good technique? But you'll at least know you're precise if you're getting about the same value over and over and over. And good experimental results should always be both. Okay. One last quick look. So let's say someone is weighing water and they weigh it 4 times. Let's say the straight line here is the correct answer. So they should be getting 25 grams. Let's just say that's the right answer. So describe A. On trial 1, they got a little more than 25. B, they got a little more than 25. Did a little less, a little less. And remember, we're going to take the average of these. So how consistent are they? Are they getting about the same value each time? They're definitely less than 26, definitely more than 24. They're very close to the same value. So they are what? Same value over and over would mean?
Accurate.
No?
I mean, precise, sorry.
Precise, good. And they're also very close to the correct value. So they're also accurate. Okay. So A is accurate and precise. What is B? Remember, these are their values 4 times. So the first time they got about 27, the second time they got about 26.8. They're getting about the same values all the time. So they are what? They are
Precise, not accurate.
but they're not accurate because they're supposed to be getting 25 and they got 27. What is D? They're not consistent, so that means they're not precise, right? They're kind of all over the place here, and they're not getting the right answer. So this is not precise nor accurate. A, B, and D are usually the only options. Accurate and precise, precise, but not accurate, and neither accurate nor precise. C rarely happens. They are not precise in C, right? They're all over the place. But what would the average be of all these numbers, if you can kind of visually tell?
Basically at 25.
Yeah, they would be right at 25. So they are accurate, but not precise. When is the only time that can ever happen? Accurate, but not precise. It comes down to one thing, and that is just plain old dumb luck. Okay. Person C is lucky. They got the right answer despite not knowing what they're doing, because all their errors just happen to accidentally cancel out. That usually doesn't happen. You just are lucky. If that person then goes and plays the lottery, I would find out what their ticket numbers are and bet them, okay? Because the universe likes them for some reason. That's all I can say.
So how many points would C get?
You would not. You would not. No, you would get some points because it's like, wow, you somehow got the right answer. I don't know how. But yeah, but not a lot. You know, this would be better because at least this, I can work with this person, you know. I can get them down because we can track down their error and get them here. This person is knowing what they're doing, but these people are random, and random are the problems. You know, when someone is random, that means what? There's no method, there's no pattern. It's really hard to fix random. But lucky is good. If I'm not looking at their work, they would have gotten full credit. If I was looking at their work, then yeah, that would be a different matter.